Hello and welcome. My name is Michael Newert. My company is Newert Electromagnetic Services and my website is emfcenter.com. I'm an electromagnetic field test engineer and I've been doing electromagnetic testing and remediation work since 1992. In this video I'm going to show you a little bit about how to shield wires, electrical wires in buildings. This will be looking at pretty much just how to shield the magnetic fields. As the name electromagnetic field suggests, there's actually two parts, an electric part and a magnetic part. So we're going to be looking at the magnetic part mostly for shielding in this case. And the electric part is another whole issue, and the electric fields have health issues as well. But the magnetic fields is the part of the electromagnetic field that has been most often linked to the very serious health effects, more leukemia and other cancers in children living near power lines, for instance. Also suppression of the immune system and lots of other health issues. So I hope you enjoyed the video, and also I want to note right now that shielding the magnetic fields is not always the best way to deal with high magnetic fields from wiring. At the end of the video I'll actually show you an example of why that is. The only time that the shielding works well, like it will in this video, is when you have what's called zero net currents and stray currents. And that means that all the electricity going through the cable is coming back on its paired neutral wire. If it's not, you get what you call stray currents or net currents. That means electricity is flowing back through the wrong wires or even through pipes and things like that. And in that case, the shielding is pretty much not very effective or even can make things worse. The shielding that I'm going to use is a small piece of what is called mu metal, sometimes called mu shield, or other things like magnetic shielding foil. And this is a 4 thousandths of an inch thick piece of material. And I'm just using a little scrap here I pulled out of my box, about 5½ inches wide by about 25 inches long. And we're going to make a little shield of that we can slide along a piece of electrical building wire. And so what I've set up here just in the carport of my home here is a length of Romex wiring, old Romex wiring. I just pulled off a job. And here's where I'm getting the power from, right from a regular electrical outlet. And in the other end of this wire I have a heater set up. This is just your regular old electrical heater that you might have to heat a room. And the reason I'm going to use that is because it's a strong load and it tends to make a big field. Now the heater is far enough away from my setup that it won't affect, won't make fields where we're measuring. We're going to only be measuring the wiring. And the first thing I want to show you is I have a little setup here. I have a Gauss meter, a very accurate Gauss meter, just about 2 inches above a section of building wiring. And as you can see, this is a very low field location right here without the heater running. We're at 0.00.1, very low field. All I'm going to do, and as you can see, even the position of the wiring can make a little difference. I'm going to twist it a little bit. Oh, I actually have to turn the heater on first. I'll do that first. We're going to come over here. I'm going to turn the power on. The switch here. We're going to come back. We should see some numbers now. Okay, here we are. I think you can see that. We're at around 16, 17 milligauss. I have this set up right now, so we're kind of measuring the maximum. If I twist this wire, I can actually get lower fields. It's just how well the two wires, the black and the white in this cable, are self-canceling. I've got it set up right now sort of for about the highest field I can measure. Right about there. So I want to have kind of the worst case here. So there you see about 17.2. Now the next step I'm going to do is I'm going to take this piece of mu metal and I'm going to wrap it around the wires and I'm going to slide it over that section over here, and you're going to see how the numbers go up and down. One of the nice things about working with this mu metal, it's very easy to shape. I can bend it. I can even put like little holes in it. It's fairly easy to work with. And it is made of about 80% nickel. I'm allergic to nickel, so I like to wear gloves to do this kind of work. Okay, I think you can see the numbers there. We're about 16.5 milligauss in this setup right now. I'm going to start sliding this little cylinder of mu metal I made towards you're seeing not much change, but pretty soon you'll see a change. Sometimes it'll actually go up at around the edge here, but here we are. We've got about, it's gone down to 9 already. 5, 4, 3, little less than 3. Now we're in the middle, so we've gone from about 16 down to about 3. That's actually pretty good cancellation for mu metal. Mu metal is never perfect, and if you get something like this from, what is that, 3/15, it's like almost like 80% reduction. That's actually pretty darn good for one wrap of this 4 mil foil. The cylinder shape is actually the ideal shape for shielding things, especially like wiring. And now we're going to see as we get to the other end here, sometimes you'll see an end effect where it'll go up even higher. See, in this case, maybe not. It all depends on the type of field. 10. It's going to start to go up as the shield is no longer there. Now we're back up to that 17, even 18 kind of level. So you can see there's quite a difference. There we go. You have like around 18 without the shielding. This one little piece of 4 mil thick foil, and we're down to something like 2.3. So we've got quite a good reduction. Factor of like 5, something like that, even 6 reduction, which is very good. And all this is a little piece of, a little scrap of mu metal. And one of the important things about this, there's about a 1-inch overlap. When I made the cylinder, the two pieces that come together overlap by about 1 inch. You need that inch. That helps the magnetic lines of force flow more easily. You don't want to just butt the two ends up to each other. You actually want to have them overlap. Okay, and now we're going to show you the kind of case where this doesn't work. Now I'm going to show you why shielding wires often doesn't work in real life and how to tell the difference when it'll work and when it won't work. So you might remember over here at the end of everything, here's this electrical heater I have plugged in. Here's just a splice I made from the building wiring to the wiring to feed the heater. And what I'm going to do is I'm going to undo the white wire. The white wire is the neutral. And what happens in buildings, this happens in real life very often, where the electricity that comes in the black goes over to the, say, the heater or a light or whatever, it comes back. It's supposed to come back on this white and continue on. And there's two currents. One comes this way, one goes this way, and they perfectly cancel each other. One makes a field, well, not almost perfectly. One makes a field that wraps one way, one makes a field that wraps the other way. The electricity is flowing at the speed of light, so it's pretty much instantaneous for this purpose. And those two fields are so close that they pretty much cancel each other. But what happens in real life is an electrician makes an error, and all of a sudden the electricity that's coming back on this white wire, instead of coming on the correct white wire, returning, instead goes on the white wire from some other circuit, or even goes into the grounding system. And once you go into the other white wires, you're starting to go through other circuits. And also if it at all connects to the grounding through this kind of error, then you're going to have all kinds of currents on things like water pipes and gas pipes and all kinds of metals in the house and the building. And it's these net currents and stray currents that are actually the biggest cause of magnetic fields. And this is even the cause of a lot of the magnetic fields from power lines. A lot of the times the power lines is the same issue. The electricity going out from the plant to wherever it's going, sometimes some of that electricity is actually returning through the municipal water pipe system, that grounded system, sometimes even through the earth itself. So those are called net currents and stray currents. And all that is, as you can see here, now the electricity that normally would go along this wire, go to this heater, come back, and instead of going back on this building wiring like it should, it's going to come back. I've just hooked up, for our purpose here, an extension cord, which is simulating like having another circuit where the wiring is coming back. It just makes a circle, comes back, comes around, and it actually goes ultimately and feeds into the same outlet where I'm getting my power from. This is what happens in buildings all the time. Okay, now we're going to set this up over here. You can see that we're still at 0.1. It's still a pretty nice low field because I don't have anything turned on yet. Now what I'm going to do is I'm going to turn on the power for the same heater again, but now instead of before, remember where we had about 16, 17, 18 milligauss with the same setup. Now you're probably going to see a lot higher level because we have this net current. Here we go. There, I just turned on the heater is on, and now what we're reading is more like 240, 250. So we've gone from a level of something like 16, 17, 18, and now from the same wire we're getting 250, 255, 254, something in that range. Okay, now the interesting thing is, with this situation and this net current, this is the kind of wiring situation where shielding usually will not help. Sometimes even it'll make it a little worse. And I'm going to now bring in my shielding material, just like I did before. Remember before it went down by a factor of about 5. And here we are, 247, 249. I'm bringing the material, 241, 239, oh, almost about the same, 251. In this case, the shielding is making almost absolutely no difference. So there's no shielding effect here. If this had been a perfect situation with no net currents, we would have gone from like 250 down to something like 50. But instead we're still at this 250, even the 259, 260 level. So the shielding here absolutely does not help when you have this net current issue. Now as we go here, we're going to see there's almost like no change as I remove the shielding material. Very little difference. That's because in this case, this kind of wiring situation, shielding the wires absolutely almost never works. You actually have to go through and fix the wiring errors and the other things that are causing the electricity to go through the wrong wires. It's only when you get all the electricity balanced and everything that goes one direction through this cable goes back the same direction, then you can do really good shielding with mu metal. But without that, the mu metal is no use at all. Okay, I hope that was helpful. It's been fun to make this video. If you ever need help designing shielding wires, you can contact me. My business phone number here is 800-638-3781, 800-638-3781. And just to remind you, I'm going to set up the old situation here at the end just so you can see the difference. And also, I just want to let you know, if you ever want to do some kind of consulting and work with me, my rate is $120 an hour. I have a 10-minute minimum, so the minimum cost is $20 for 10 minutes. And sometimes it's just like a half an hour to go through the wiring, what you can do about it. Typically, often to shield wiring, we're looking at a consultation of an hour, hour and a half, 2 hours to do it really well. Okay, hope this has been helpful. That does a pretty good job of shielding the fields. One more time, put the shielding back, and even how I arrange it a little bit all makes just a slight little difference, but pretty much we're going from something around 16, 17, 18 down to around something like 3, a little less than 3.